Welcome back, everyone. I'm your speaker today, Onri Jay Benally. And today's lecture, the topic is going to be on the control hardware for quantum chips. This is the final lecture, part 5 in the lecture series called Quantum Hardware, or Quantum Hardware Engineering and Development. So that's what we're going to be covering. And of course, there are key terms related to the manipulation and the capture of these quantum devices. So, again, my name is Onri Jay Benally, and I'm in the first year of this PhD program at the University of Minnesota. And the PhD is in electrical and computer, or actually it's just electrical engineering, a PhD program, but the focus for me is on quantum hardware, the engineering of quantum hardware. And that is related to computers here. But regardless, our department is called the Department of Electrical and Computer Engineering. And I've been here at the university for the past 5 or 6 years. And I've been here since I was an undergraduate. So even though this is just the first year of the PhD program, the end of the first year, I have been here since I was an undergraduate doing research work on nanotechnology related to spintronics, what we call quantum spintronics. Our laboratory is called the Nanomagnetism and Quantum Spintronics Laboratory. And the leader of the laboratory is my advisor, my principal investigator, Professor Jinping Wang. He is the Distinguished McKnight University professor here at the university. So we work on, well, the manipulation of spin states in nanomagnets, which are essentially crystals of metals, and then we can fabricate them in the laboratory, and that's a big part of my work, which is nanofabrication engineering as well. So here's a table of contents. We're going to go over like a background and motivation, and then that will help us get a ground or base understanding of what's to come throughout the rest of the lecture. Also, one more thing to note is I try to improve the microphone quality here, so hopefully the audio is much better for this recording today. And just wanted to point that out. I hope you might notice that the audio is improved. The other thing I want to note is that, well, I tried to introduce the laser pointer here to make things much easier to follow as well. Okay, so moving on, the quantum hardware, of course, consists of, when we move on from qubits, the basic idea of qubits, we need to turn into some kind of gate to do quantum computation. And so we're going to outline some examples of quantum gates and show the representations of those logic components. And then we'll talk about some visualizations for those qubit states that come from quantum gates as well. And then we'll use that to segue into the quantum stack, which is more of a revisit for the third time, so that you get a really good understanding of what the quantum stack is all about. And of course, within the quantum stack, we do some kind of manipulation, measurements of qubits, and in order to do so, we need the hardware, and we also need to interface that with the software, which is all part of the quantum stack. And so that leads us to the quantum system configuration. So when I say configuration, I'm just talking about the system setup, the hardware, like the physical machine. It's actually set up and built in a laboratory or some other facility, and we need to know what that looks like. And then that leads us to the analog equipment. So the analog equipment, that can be bulky, or so if you want to control like individual qubits themselves, or individual logical qubits, but you can only do so much. It's kind of like doing manual labor in this case. You can control it one by one, and it's all manual or semi-manual. But if you want to scale up qubits, you need to be able to automate something, and you need to be able to map out everything on a chip, and you need more than just a few wires, a few cables, or a few dozens of cables in order to interface with what is eventually, or what am I saying here? What will inevitably turn into 1,000,000 qubits. So if we're going to do 1,000,000 qubits, we need some kind of control interface that will be compatible with that. So that's what we call cryogenic compatible CMOS. It's just a semiconductor chip. We'll get more into that. But regardless, there are some other fun examples that we can talk about and explain, which involves audible, like music. You can create music from quantum systems. And this is just another way of learning how to play with quantum states. And then we'll talk about the conclusion at the end. And then we'll summarize some things. So here is a signature style of mine, which is to introduce an image into the table of contents slide. And this shows a picture of Dr. Jerry Chow at IBM Quantum. So this is a quantum processing unit called the IBM Osprey, and this processing unit has 433 qubits. And we also have a map, or a layout, a sort of a timeline of how this qubit came to be, and all of the predecessors to this qubit, which are many of which are still used and employed in quantum computing, the quantum computing community, available on IBM Quantum. All right, so this slide here is just showing an introduction of the different kind of bits that exist. And of course, it all began, we have this switch, this excited state and the ground state. Ground state typically means that the switch is turned off, and excited state typically means that the switch is turned on. And so if you only have these two states, like a polarity almost, like, you can think of it like a polarity, then what happens is you can create a logical bit, a binary digit. So binary digit is the full spelling of the term for bits. So if you were to collapse this term altogether, it becomes bits. And then the same goes for p-bits. The full spelling of p-bits is probabilistic bit. And the probabilistic bit is a modified version of this switch here. So this on and off switch here is the same, it's the same configuration here. You're turning on and off the switch, but the difference here is that it fluctuates back and forth between on and off very rapidly, and oftentimes this can be at random. And so the probabilistic bit is randomly switched on and off, either through thermal fluctuation or some other means. And you can actually calculate or count the number of times that this switch is turned off, or the number of times it's turned on. And this probability can, when you add it up, it should all add up to, it should sum up to about 100%. So out of 100%, how many times does this qubit exist in this particular state, and how many times does this exist in this other state? So this bracket here is not showing exclusively how many times this switch has been turned on or off. It's just showing an example of what that probability would look like. So here on the right, this is what is called qubit. So the qubit comes from the full spelling quantum bit, and the qubit is typically represented by this so-called block sphere. So this is a sphere, a drawing, a mathematical drawing of a sphere, a ball. And you can see that there's an equator noted by this dotted line. So you can think of this dotted line as the equator around this sphere. So this sphere contains sort of a north and a south. I know it sounds kind of backwards, but think of this as an upside down magnet, maybe an upside down planet. The ground state or the off state is up here, and the excited state is down here, as it's represented. And it also can exist in infinitely many other states, So what you have to do to get to that is you have to pick a point. So I highlighted here in blue. There's a blue point, and you can pick any other point around the surface of the sphere, and that point will be able, you can extract, will give you the ability to extract information such as the phase information, and also the distance or the angle of which that information, the distance it is from the ground state or excited state. So it's you can turn it into like a relative representation. So this particular state is like maybe you could say it's in a particular percentage related to the zero state. So in the zero state, this particular state exists maybe 70% or 80% in the zero state, and complementary on the other side, it is like 30% or 20% in a different state relative to these other states. So you can represent it as such, and this is how you get is how you represent a quantum bit. There is like this equal probability that exists 50% around this equator. So if you pick the equator point here, any point around this equator, then that would be considered a 50% probability of existing in either one of these states. So you can use that to represent some kind of qubit device. And eventually here we have some history, historical background, and there was a famous scientist by the name of Richard Feynman back in 1982, and he introduced this idea, along with some others, on quantum simulation. So basically he says that if we're going to be able to calculate or try to simulate or represent nature truly as it is, then we need to use objects in nature to create those representations, and we also need to extract information from those fundamental from those fundamental components. So in this case, we need, since we know that quantum mechanics tells us about the most fundamental parts of nature, or fundamental parts of the universe as we call it, then we need to use or create an object that utilizes quantum mechanical effects, and we need to be able to exploit those properties, those quantum properties, to do computation and to extract quantum information, manipulate quantum information, and so forth. And through experimentation and proposals and using physics, it has been determined that we can create such an object called qubits. And as a physical device, it needs to be able to oscillate. So that oscillation is called a n-harmonic oscillation, or if you're talking about the device itself, it's called an n-harmonic oscillator. So the n-harmonic oscillator, of course, can happen within an artificial atom, so which is like a physical device, a nanoscale object or a microscale object with nanoscale features in it, or it needs to be made of natural atoms. So there are natural atoms which have, resonant frequencies, and they can have these oscillations that exist in these atoms that are n-harmonic. And so we can use those oscillations in either these natural atoms or artificial atoms to create a qubit. So here, this is just an electrical representation of an oscillator. So of course you have like an inductor, capacitor element, and then you'll be able to fluctuate energy back and forth, convert between magnetic energy and capacitive, so like charge energy in this capacitive element that will release and then store here, and then just kind of loop back and forth. And so then you end up having an oscillation, and you can measure that oscillation at the end as a pattern like this. So this slightly dimmed, or this slightly faded representation in the background, you can see here it says harmonic oscillator. You can see here again there's an inductor or capacitor, and you're measuring these resonating frequencies out of that harmonic oscillator. this electronic device. And that harmonic oscillator is going to have equally, what we call equidistant resonating frequencies within that oscillator. And you can use that as motivation to again take something like an artificial atom or a natural atom and create such a diagram with resonating frequencies as well. But you'll notice over time that by manipulating a device, maybe the physical properties or so, you will get a resonating frequency that is not equally distant. So these resonating frequencies will have separate distances, and as time, or should I say not time, but as you increase this, measure the higher energies within this oscillator, then you will notice that the distance becomes smaller and smaller. So this is just a representation of a qubit that has this ground state and the excited state. So you can also extend that to make Q-trits and some other kind of quantum bits that have, maybe not necessarily quantum bits, but quantum trits, quantum quadrats or something. I forgot the name of the fourth one. There's a different one. It has 4 quantum states, and that would be represented by these excitations, by these resonating frequencies. So that's what we get it from. And then the coherence time, of course, this is just a representation of what is called a kind of Moore's law, because for semiconductor computing, for classical computing, we do have a Moore's law, and it's very well known. But for quantum computers, there also exists some kind of Moore's law, and that's why it's in quotations here, of the progress that has been made for building different kinds of quantum computing components, the quantum bits. So these are the various kind of quantum bits that have been experimented on over the years. But you'll notice that as you increase the quality of the qubit ever so slightly, even just a small amount of increase in quality will have really huge advantages as far as the overall usage of qubits as quantum gates. If you compare that with semiconductor processors or classical processors, that doesn't happen there. If you want to do like some big improvements, then there needs to be some large improvements overall on the quality of the device, and you need to do some quality control, and then you need to also do like some kind of benchmarking to really improve all of these transistors in those devices. But for quantum computers, for quantum bits, every small increase in quality affects the entire architecture. So it's much more dramatic. That's something you should note. So here's some more background. Basically, we have some scientists, Daniel Loss and David DiVincenzo. This is the same DiVincenzo that created the DiVincenzo criteria, which is a list of important ideas, not ideas, but like a list of items that it's like a checklist really, that shows what should be or what defines a quantum computer. And if it checks everything off for that list, then officially it is a quantum computer. So these two scientists introduced this idea of using electron spins to do quantum computation way back in 1996, which is roughly the same year I was born. And so these are some critical efforts to realize physical qubits. And then Bruce Kane, another scientist, developed this donor spin model, which is using that idea of electron spins to create a qubit. So basically what he did is create a model, a simulation, sort of like almost an elemental method, but a a representation of the physical qubit in a 3D diagram, and then that diagram, you can use it to try to represent a physical object. Because of course when we're designing something, oftentimes in the laboratory or even at home, if you're designing something, typically you want to visualize it somehow, and you want to be able to show the progress that has been made over some amount of time. And this can be done through either 3D modeling something before you build it, or taking a picture of something, and then that picture will typically be of some form of model, a physical model that you can build, a smaller model of what you're trying to represent, and then use that model as a way to motivate what you're trying to build. So that is more or less the same idea being used here. You create a donor spin model, a 3D model of what's supposed to be a quantum dot, and sort of the readout methods and the physical ways of trying to stimulate that physical object. So in this case, the quantum dot is just a nanocrystal, just a nanoscale object, and if it resonates at a certain frequency, then we can do so using magnetic resonance, and this was considered a hybrid scheme. So quantum states, of course, they are represented as vectors. These are just mathematical representations, and the representation is just there to help you create a map of what's happening. Again, you need to be able to visualize something before you actually try to build it or manipulate it. So for quantum states, it's the same case, but it's done with mathematics. And qubits, on the other hand, are also represented as such, mathematical representations, which are matrices. This is the same matrix that is used in linear algebra, and for that reason, quantum computation, quantum computing in general, tends to use a lot of linear algebra concepts and ideas. It's the language. So if you want to manipulate those qubits or quantum gates, you can represent them as matrices, and then if you apply that to a quantum state, then you can manipulate those vectors. So of course, when we talk about physical and logical qubits, you can try to group a number of qubits together to represent a single logical qubit, which is the computation element used in the processor itself. And you can use a single physical qubit if you want to represent one logical qubit, like a 1-to-1 ratio, or you want to improve the accuracy of the overall computation, then you can group together like 1,000 qubits, 5,000 qubits, or even more than that. So these are all ideas that lead up to what is called error correction. Passive error correction, active error correction, there are different methods, and there's a big effort in that area of work when talking about quantum technology or quantum computation. And so we're not going to be talking about that today. I believe there's a lecture, another lecture series available on QuantumGrad if you want to go see that. So as far as the simulation goes, so like this is what Richard Feynman was talking about. He was saying that we want to be able to try to understand nature better and try to simulate what's happening in the real world. But in order to do so, we have to create something. So we have qubits, and let's say we have qubits and they're nice quality. But if we only have up to like 50 qubits, let's say you had some money and you had the budget to build 50 qubits, or maybe you had the budget to build a certain number of qubits. Let's say they give you the option between buying 53 qubits and 63 qubits. So there's a huge difference between having this amount of qubits here versus other amount, and that is its ability to process a certain amount of information within a given time. So of course, for a classical computer, a CPU, you can do some kind of calculation that is done on like 128 bytes, for example, and that can be done in roughly 2.6 microseconds. And if you wanted to process like maybe 137 gigabytes of random access memory on a classical computer, then that can be done within roughly 4.6 minutes or so. And that is fairly efficient. And if you try to do that same thing on a physical qubit system, then you could do it with like 40 qubits. But on the other hand, even 53 qubits can only take you so far, and that's something you could do within about 600 hours, 625 hours in this case, on a CPU system. So that's the difference. However, if you start to gradually increase the number of qubits, or the quality of the qubits along with the number of qubits, then you can keep the processing time relatively consistent. So it'll take you about 15 minutes to maybe 2 hours to process something that is this large on the order of exabytes. But to process exabytes amount of information on a classical computer, it starts to the efficiency starts to dwindle very dramatically, and even to the point where it seems relatively impossible, because how are you going to do that amount of computation in that amount of time? Because is human society even going to be here around that time? You know, you ask questions like that. Regardless, things happen, and we can save a lot of time by using a certain number of qubits with a certain amount of quality. So if we keep the quality consistent and increase the number of qubits, then we can start to realize these large computational advantages. So with that, let's talk about quantum gates. So here are a list of 5 qubits. So these qubits, of course, individually have matrix representations. Representation here is showing like the different things you can do, and if you apply this matrix representation to some vector representation in a bracket node, like a bracket or some other small matrix, then it can manipulate that. So here, typically, the 5 basic qubits exist in combinations of 1 or 2. So here you'll notice that there's a single line showing behind this box. So that single line represents that there is a single qubit. So this is 1 qubit, 1 qubit, 1 qubit, 1 qubit. But then there's this qubit here, which is called a controlled knot qubit, or C knot, and this consists of 2 qubits. It needs 2 qubits because in order to control what's happening on 1 qubit, you need to apply this gate that is manipulated or controlled by the other. So these qubits will influence each other, and you can use that as a gate to manipulate quantum information. And you can also extract quantum information afterwards simply by reversing the order of those qubits on a circuit diagram. So you'll see here examples of how these qubits are placed in a diagram. So typically from left to right, the qubits that are placed, or the gates that are placed on this diagram, it's a time representation. So from here is the beginning time, the start time, and then the end time. It needs to go from left to right. So that's how you read these diagrams. They're kind of like music sheets. Think of these as fancy musical sheets, musical notes being applied. You need to read it from left to right, and if you skip something, then you need to go back and fix that. Regardless, this is just a way, like if you wanted to create a Bell measurement, a Bell state, then you can apply a Hadamard, which will allow you to create a superposition, 50% probability, 50-50 of 0 or 1. And then you can connect a C0 quantum gate onto these 2 qubits, and then what happens is you'll be able to create that Bell state, and then you need to apply a measurement gate at the end. So this is just a way of representing some basic quantum bits, some quantum gates from quantum bits, and you can decode or encode information in these simple diagrams, relatively simple diagrams, simply by placing these gate representations in a certain order. So here's a visualization of qubits. As I mentioned, we have the Bloch sphere. On this Bloch sphere there's a surface. So the surface of the sphere, you can select a point, and then you can use that point and extract information from there and represent it as a wave function, or well, this quantum state here is there's this bracket notation, and then you can summarize this as a probability of either 1 or 0 state, the ground or excited state. And what is that? How does that add up? It should be add up to 1 actually at the end. But regardless, this Bloch sphere representation is just a way of representing a single qubit, one qubit. But if you want to represent multiple qubits, you need to use other methods. So here's one method. It's called a Q-sphere. So the Q-sphere, it also is a sphere, of course. It's got a surface area, a surface, and you can pick any point on the surface of this sphere and you can extract information from it. So this Q-sphere representation uses a color chart, a color label, to represent the phase information. So the phase information is just around this. So like there's a x, y. So here you can see in this direction there's an x, in this direction there's a y, and then there's a z component, x, y, z component. So here there's also an x, y, z component, more or less, and relative to either of these three components, there will be some kind of phase information, which is an angle relative to one of these x, y, and z components. And that phase information will be able to tell you what kind of state that this particular qubit exists in versus this other state versus this other state. So many of them, many qubits, can be represented on this single Q-sphere. But on the other hand, if you want to do like a 3D bar chart, you can do so. You can also do a probabilities view on a bar chart as well. It's a 3D bar chart. I drew it here in 2D because there were too many diagrams showing up on this page, and I wanted to show everything on one page. But regardless, there is a bar chart, a bar plot, a diagram representing those multiple qubits, and you can do so. And the other experimental way is to use a fractal representation. It's a bit more artistic, but one of my friends from IBM, Victor, he also has some tutorials and sort of guides to show you how to do fractal view representation of qubit states. That can be done in Jupyter Notebook or some other program where you can host Python. And so here's an example of those qubits being represented and being applied with a qubit gate. So here is a start in the ground state. So so this particular example shows a qubit being initialized in the ground state, 0. And then if you apply a Hadamard, it's going to place it on this equator. So when it's on the equator of this sphere, that means it is in a probability, a 50% probability of being 0 or 1. And when you apply a Z-gate, which is just a phase flip gate, what happens is it's going to flip the state of that qubit 180 degrees relative to this position here on the equator. So if it's here in the x direction, then when you apply the phase flip gate, it's going to flip it to the other side. So that's what's happening here. 2 different kind of qubit gates have been applied to the initialized 0 state. So that's just some basic introduction of what you can do with qubits, represented mathematically, of course. And then here's this representation of what is called quantum volume. It is just a number. It is considered an arbitrary unit, AU, and it's also, you can also consider that a non-absolute metric. It's just a way of showing you whether or not a qubit has a particular quality. So if it's high quality, it has a high qubit volume, a high quantum volume. If it's low quality, it has low quantum volume. So this means that if you have a certain number of qubits, then the quality will hit a peak. So the peak quality for this number of qubits, it stops at about 5 qubits. But if you have a higher quality qubit, then the number of qubits will only take you up to about 15. So the peak quality exists here. And then the same goes for other higher quality qubits. So if you have a qubit that has really high quality, then the quantum volume will be very high, meaning that you can increase the number of qubits and still be able to do a large amount of high quality quantum computation. So in this case, the quantum volume again is just representation of such. And you might also have heard of this term called CLOPS, circuit layer operations per second, which is an effort to make quantum bits, or the fidelity, the quality of quantum bits, much more formalized, to make it much more, well, standardized. Standardized meaning you want to be able to use it everywhere, and it should have some kind of physical value, or not physical value, it should have some value to it that you can use maybe in terms of energy efficiency, things like that. So that's what this slide is about. And of course here again, as I mentioned, this is the third time we are introducing the quantum stack. The quantum stack, we have software components and we also have hardware components. So this lecture series has entirely been focused on this hardware, on the quantum control hardware, and also the quantum hardware, the quantum bits, the hardware for hosting the quantum bits themselves. You can see that here in this diagram, this is just room temperature components here, which is also control hardware. 300 degrees Kelvin is room temperature. That is representation of what is room temperature, which is roughly about 20 degrees Celsius. And here these two blue boxes just are representations showing that you can place the components inside of a cryogenic chamber, low temperature chamber. And this chamber, you can see here in this blue box, this light blue box, there's 10 millikelvin temperature, so it's really cold here. And here's the quantum chip itself connected to all of these interface components. And then here 4 degrees Kelvin, so this is still within the chamber itself, but not quite as cold. And you can place components here as well, and there have been efforts made to place the cryogenic CMOS components here, or even place them down here somewhere within the much colder parts of the chamber. So that's what this is to help represent. Now I'd like to show you an example. This is an example that shows a neuron. So neurons, of course, exists in relatively every sentient being. You have it in your brain, I have it in my brain, and our brains consist of all these complex networks of electrical signals, and you can also stimulate those electrical signals in the brain by using a chip like this. So that's why we have brain chip. That's why there are companies that try to focus on using nanotechnology or microtechnology to create these probes, these nanoscale probes or microscale probes that can stimulate the individual neurons. So in this case, this example, this experiment shows a chip, and the chip has a series or an array of neurons. So you can place a neuron, a physical neuron, from the laboratory, and then you can stimulate the neuron, and the neuron will fire a response back. And you can see that here plotted on the right side. And you can do that measurement over and over again. When you stimulate the neuron will fire a response back again and again and again. And as you overlap those readout measurements, you begin to see this pattern, this consistent pattern for each of these diagrams. So this is a measurement of 5 different neurons, and each of these neurons has this particular response, this electrical impulse. And the same goes for quantum bits. Quantum bits also can respond to a signal. You can stimulate a qubit and it will respond with some kind of signal at the end. And you can think of it as, you can think of this as an analogy for that. So here, this is what I'm talking about. Here is a signal. This is the pulse signal, and typically this is within the microwave frequency or radio frequency, maybe megahertz or gigahertz or so. Specifically when you're talking about spin qubits or superconducting qubits. And of course when you're talking about other kind of qubit platforms that use some modulating signal or stimulating signal, those can be easily made compatible with. This is just a basic example of what a qubit. This is again the mathematical representation of the qubit, what the qubit looks like on a Bloch sphere. And what's happening is you have an initialization, and the manipulation is coming from the actual pulse. So this pulse here is being applied to the qubit, and then the qubit will respond by sending a signal back to the control hardware, and that signal will give you a readout, and then you can plot it on a graph like this one, for example. So here, this is just a 2D diagram of these microwave pulses, these burst durations on the order of microseconds. So you can see here there's a bright spot. There are some bright spots in this diagram, which is called a chevron diagram. But these bright spots represent a probability of the spin states being in the 1 state, or close to the 1 state, or should I say the excited state, or should I say 100% upstate probability, or close to it. And if you select a microwave frequency on the order of gigahertz, so if you were to select somewhere between 18.5895 gigahertz and somewhere between 18.5890 gigahertz, somewhere between this range, then you should obtain some kind of spin-up probability. And that probability can be selected within this range, this microwave duration range, somewhere between maybe half a microsecond to up to about 1 microsecond or so. And if you pick that spot, then you will get this probability. But if you want a spin up or a spin down probability, then you can select a slightly longer microwave duration within this frequency range here, and you will get that probability. And this is just a pattern of that sweeping microwave. And here, this diagram on the top, this plot is just showing sort of a 2D slice. So if you were to slice this, take one slice out of this diagram, then you can use this. This is like a cross-sectional view slice of this diagram here, and then you can represent those qubit states as well in the same way. So these are more or less two different representations of each other, but on here, this is like multiple measurements being done over a given time to create this graph. But this measurement here on the top, this is like a single measurement. So more or less a single measurement. And here's another analogy I want to introduce. So I'm a musician, and I play the Hammond organ. This is called a 1957 Hammond Z3. And this organ it's an old machine, old device, but it has amplifier components. Because it was built so long ago, it has vacuum tube components, because vacuum tubes were fairly prevalent in those days, in the 1950s, all the way back to the 1930s and 20s or so. And the vacuum tube components, the vacuum tubes can essentially do many different things. They can do amplification, rectification, and a number of different things. But ultimately, what I'm using this for is to amplify a signal that is coming from the keyboard. So this organ, I can press a key on here, and what will happen is there's a preamplifier in the back which will amplify that weak signal, and then that signal will come here and it will turn into audio signal. Well, actually, it goes into this tone generator inside of the instrument, and then the tone generator inside of the keyboard itself will send a signal to the preamp, and then that will go out to here, which will be amplified into audio. And then the audio frequency here, we can hear it as music, beautiful music, very beautiful. And you can create really deep bass frequencies, but that's besides the point. And here's a similar diagram. This is a layout of basically what's happening here. There's a keyboard. You are interfacing with the keyboard by touching these buttons, turning knobs, switches, and pressing the keys. And you can create music out of it. And what that's doing is it's sending a modulating signal to this digital interface. So the digital interface might also have a signal generator or a series of stored sound samples, audio samples on here. But in order to activate those audio signals or to modulate the frequency of those audio signals, you need some kind of input, which is provided by an electronic keyboard here in this case. And what that does is once you obtain that modulated signal, you can plug it into this wireless cable which goes to a mixer. And a mixer is just there to organize the sound signals into these speakers. So these are considered a transducer, or a kind of device that uses a magnet to move a electromagnetic coil, to move a speaker diaphragm that we can hear the sound from. So the sound that we hear in the end it goes through all of these series of steps from this musical instrument system. So the same goes for other instruments. So you could in principle have something like a guitar on the outside and then plug the guitar cable into this digital interface. But the difference would be that the guitar already has signals being generated from it itself. It's just that that signal is being converted into electrical, and then that electrical signal goes directly here and then amplified. So as a result, you can have a very simple system if you have a guitar setup, electric guitar setup, because the signal is ultimately being generated from the instrument itself. Whereas for this instrument, the signals, the musical generation is not always being generated from here, especially for MIDI instruments. But however, if this is not a MIDI instrument and the sound signal is coming from here, then that's fine as well. It still will send a signal that will modulate what's happening inside of here that can be amplified. And the same goes for whatever's happening here on the left. And these are all familiar ways of trying to use instruments in the real world. And the same goes for this setup in our laboratory. This is our magnetics laboratory at the university, and what you have is a PC, a desktop PC, and as a keyboard you can create algorithms, you can create a series of steps that will automate. You can create automated steps and design them either through like code in Python, or it can be done with some other interface like LabVIEW. All of these can be programmed on this PC, and then that PC is plugged into some cables that interface with this analog to digital interface, and then from there that goes and plugs into this waveform control, which is connected to a power supply. And so this is where the high frequency signals are coming from at the gigahertz range. And then if you want to modulate that signal or modify that signal, the waveforms, then it needs to be plugged into these other components here. And then from there you can plug it into the testing stage where the chip is ultimately located. So you can place a quantum chip here, a nanomagnetic chip here, some other chip that uses microwave frequency, and then you can use that microwave frequency to test or excite or stimulate that quantum chip, the physical device, and then that device will send a response signal in the end. And that response signal, it will be detected here by this setup here through the nanovoltmeter, and then the nanovoltmeter will send a signal back to this interface which goes to the PC, and then you can start to visualize, or you can represent those signals on a 2D graph on the PC, and then you can collect the data and then present and publish about the data that you studied. You can do post-processing analysis, do all the math that you want at the end. So that's what this is about. And then here, now we can see what the qubit system looks like. So we have some analog components. So this is a control component for the qubits. The qubits would exist here at the bottom of this cryogenic chamber setup. So this chandelier, it would have a chip here, and then the chip would be connected to these series of cables, and the cables could be connected to a cryogenic CMOS. This one I don't think necessarily has a cryogenic CMOS component in it, but if there was, it would be placed somewhere here or maybe down here, and then that would interface into this device here, and then this device ultimately connects to a PC, a desktop PC. And what that looks like is you have software, and the software is programmed. You can program the qubit algorithm, the quantum algorithm, by a series of quantum gates, and then you can represent it by this visualization here, and then that is parallel to these signal outputs. So the drive outputs, or the drive signal that is coming from this machine, this component here, is being modulated, and it's being taken from this algorithm. So the algorithm from the computer will go to this machine right here, and then that will produce these specific waveforms and pulses that will excite the qubits that exist on this machine, on this quantum device. And these qubits here, there are two of them. They look like crosses. They would be stimulated and excited by these pulses, and then they will send a response signal back, and that's when you can take the expectation values. Like, you can extract information from those response signals coming from that physical device. So it's almost as if the qubits are alive in this case. The qubit is living. It's not really alive, but it's almost as if it's alive because it's responding. And as a result, you can plot those measurement results on a Python chart. So this is a Python plot showing the two different states, the ground and excited states, and then you can do that measurement over and over again, and when you keep doing that many times, it will create this sort of scatter plot, and then you'll see this group of plots, groups of data being plotted here in these two different areas. And so you can actually differentiate between the two. You can identify those two. So again, here is the qubit control hardware from this company called Qblocks. And then here is the PC, the laptop, the desktop PC. Well, it's a laptop. And the laptop, it hosts the software. In this case, the software is run on a Jupyter notebook. The Jupyter notebook is just an software environment that can host programs like Python. Python is heavily used here, and the Python, you can use that to automate the quantum algorithm, automate the series of steps being taken in those quantum algorithms. And then you can use that to do computation and do the readout back and forth between these two machines. And then you can use that to control the qubits. So that's just a basic example. And now we'll look at the quantum systems. So of course, the quantum control components, they exist in various sizes. For typical classical control systems, even for classical computing schemes, you can have a desktop computer, or even smaller, you might have something like a phone, like a mobile device. And the mobile device, it can have quantum devices on it, but not necessarily for computation as of yet, because the control components are, we're only going so far with them for now. So let's see how far we can go. Here on the right side, you can see for this system is like a server farm, and supercomputers have a similar setup like this, where they have a bunch of racks connected together in a large room, and it might take a lot of energy to keep this facility running. The electricity bill could run so high, and well, you can do some really useful things, some powerful things with that computation supercomputer. On the other hand, you could create a quantum computer that uses a similar setup that is more server farm like. So server farm is just a bunch of racks like this, which all individually host some quantum hardware setup. So the hardware setup is connected to another quantum hardware setup, connected to another, and so forth. So you could store this in a small room, and it would have the same power as some of the largest supercomputers in the world. So for that reason, quantum computers have been said to have been also called supercomputer simulators. They're able to simulate supercomputers with much smaller sizes. You can also try to miniaturize the quantum computers by placing it in a desktop machine like this, and all the control components can be miniaturized using semiconductor chips. The control chips will control the qubits, because as I mentioned before, the qubits themselves, they're small chips that you can hold in your hand, and in order to control that, you need to interface it with something that's useful. So in this case, it can be done with semiconductors. And then here is just a representation of a generic representation of how the classical interface is placed next to the quantum processor. It might be placed next to the quantum processor or some distance from the quantum processor, but regardless, what's happening is you are sending a signal, modulating signal from the control hardware, and then that goes into the qubit, and then when the qubit gets excited or it gets manipulated in some way, you're manipulating quantum state, then it will send a signal out, and then you can do the readout, and you can amplify the signal, that weak signal, and you can try to plot that on a graph. So here, this is an example of a qubit control system that has been implemented in this diagram. So it is called a single chip CMOS, a single chip quantum CMOS. So this processor, the quantum processor, exists right next to the classical controller. So there's a CMOS chip that has all of these drivers on it and detectors, the inputs, or should I say the outputs and the inputs. So this is actually the output, and this is the input, because the detector will in the end send a signal back to the PC. But in order to do so, of course, the qubits, it's got to be wired up somehow, and when you do it on a CMOS chip, it's just, well, wires. The wires that were micro-patterned, fabricated onto the chip, and then you can try to place as many components that are compatible on this CMOS component. And so here is an example of this, what such a setup would look like. It's a desktop-sized machine. Of course, we see this is prevalent everywhere, where there's a quantum system with a chandelier, and the qubits exist here at the bottom, but all the control hardware, they exist somewhere up here, or even outside of the chamber. So here, this is a representation of such a setup, and here it says that there's a integrated circuit that is compatible with the CMOS in this part of the chamber. So this is one of the examples that I was talking about earlier. And this is another setup showing what Microsoft Research has been doing to put a CMOS component, the controller chip, next to the qubit setup. So here's the quantum processor or quantum device, and then the quantum device is connected to, wire bonded to the CMOS controller. So all of this is on one single package, on one single PCB component. And all of these are cryogenically compatible, of course, and you can place it inside of a chamber, and then from there you can wire bond all the components here into some pinouts, into some interfaces, which will eventually connect to some other smaller cables, a smaller arrangement of cables, that is, maybe fiber optic cables or some other coaxial cables that will connect to a PC, a laptop, or a desktop PC. All of that which is contained somewhere up here. So this is just such an example. And here's another setup showing you have the qubits at 10 millikelvin, and then the control setup, the controller CMOS chip itself, cryogenic compatible CMOS. This one is designed to work at 3 degrees Kelvin, so that will be placed somewhere up here. 10 degrees Kelvin might be too cold for this chip, so they place it somewhere up here instead. And then this is just a layout of how the control setup looks like. So for here, we have a cryogenic CMOS setup. So this is the PCB, this is that same system, and then there's a spin qubit that is hosted on this chip, and the PCB is in this case meant or designed to be cryogenically compatible. So if you want to do measurement, you can design a PCB, and then you just have to make the PCB compatible with low temperatures. And here's another example. This one uses cryogenic CMOS, and again, I believe this is done in collaboration with Intel, and this is, I believe, called a Horse Ridge. So this Horse Ridge CMOS chip contains the digital analog components, the converters, and it also contains some memory components. So I guess you could call it cryogenic memory. And this is the layout for such a chip. What this is supposed to do is control the qubits. It might be placed next to this qubit chip layout, or might be, or in the future you might be able to place the qubits on this same architecture. It's just that you need to, like I said, make a cryogenic CMOS compatible component. But not all cryogenic CMOS components are, not all of them can operate at such low temperatures in the millikelvin range. So that's another challenge that's being addressed and researched at the moment. And of course, you can obtain the readouts and try to measure the spin up probabilities. So here's a 1 excited state or spin up probabilities at a specific frequency. So in this case, 13 gigahertz, and then that can be obtained from this single chip without having to connect to a bunch of convoluted control systems that we typically see in conventional setups. So here's an example again. This one shows the FPGA control of the quantum system. So if you have a quantum processor unit, you can place it in the chamber and then place the FPGA board, a field programmable gate array. So this is just a programmable processing device, a processing unit of sorts, somewhat like a processing unit. It's programmable regardless. And this device, this processor, will have all these control components that are, again, programmable. You can make it do whatever you want, and then that will interface with all of these amplifiers, inverters, filters, and so forth. And then that goes to the qubits themselves. And so if you wanted to do, maybe you know how to do your own programming of FPGAs, then you could you could probably buy one or build one yourself. I think building one is fairly complicated, but if you wanted to buy one, you could get an FPGA board and then interface it with all these other components, and then if you know how to build a quantum processing unit, or if you can get your hands on one, well, by some chance or probability that you happen to stumble upon the quantum processor unit and you wanted to do this at home, then you could in principle use an FPGA board, and you can program it like this, and then you can take the measurement readouts of the qubits without having to use a bunch of coaxial cables. Or if you do use coaxial cables, it's up to you. You can switch them out with fiber optic components to make things a lot easier and deal with less noise, but that's besides the point. So here, again, this one is commercially available, off-the-shelf cryogenic CMOS components. So this CMOS component, it can handle down to about 50 millikelvin. And as a result, you can place the CMOS pretty much next to the actual quantum processor. So if you have a quantum processor, you can place it here at the bottom of the device. And then this DUT, it represents, it's just an abbreviation for device under test. So whatever quantum device you have, it could be a quantum processor, it could be a quantum sensor, or some other device that has a need for being tested by this cryogenic CMOS. You could configure it as such and then connect all the cables on the outside. Like I said, you could do fiber optics if you want, and then you can set up the control system at room temperature, all of this connected to a PC, and then the PC will control this cryogenic CMOS component. Again, like I said, it's something you can buy off the market. And then here, again, another setup that uses FPGAs. So the difference here is that the FPGA is at room temperature outside of this chamber. So this chamber is actually pretty common. You could buy a chamber like this for a laboratory, and these chambers are available in many different laboratories, physics laboratories. I think even some chemical engineering laboratories have such a chamber like this that has liquid helium. So this liquid helium chamber, it has this rod that you stick inside of it, and then at the end of the rod you can place the PCB that hosts the qubits, and then at the top of that rod you can have this connector box that allows you to interface with all of the measurement setups and also the FPGA board, which is going to send a modulated signal from a PC, a laptop PC or desktop PC, into these line-in connects. So this is an example of what those cryogenic CMOS components look like. So this cryogenic CMOS here is an amplifier component, which is one of the components on this PCB. So you can see here, top view, bottom view. And then here's a comparison table, a chart showing the various kind of interface electronics at cryogenic temperature range. And these kind of cryogenic CMOS components, they are compatible with different kind of qubits. So it looks here that they are primarily associated with transmon superconducting base qubits and also spin qubits as well. So perhaps there are some others that are aimed at other platforms, but these are the two primarily ones that are compatible with cryogenic CMOS. And these are all the other properties that are associated with these different cryogenic CMOS components. And then you'll notice here one that can operate at temperatures of 77 degrees Kelvin, which is a little closer to liquid nitrogen temperatures, whereas these other ones are more around the liquid helium temperature. And liquid helium is, I believe, slightly more expensive. Maybe not slightly. It is more expensive than liquid nitrogen. So this might be a cheaper option for you if you're working with superconducting qubits. So here's an example. This is pretty much close to the end of the lecture series, lecture presentation. So this is something that has been done at the Yale Quantum Institute. And what they've done is they've created a concert or a live performance taking information from a qubit that is over here connected to a quantum computer, and then that information is plugged into a PC, maybe through the internet or some could be remotely done, but regardless, you have some quantum computer and it's connected to a computer, a PC, desktop PC. And then you can use those signals, and then you can take measurements of those signals and try to identify the waveforms of those signals, and you can also reduce the frequency of those signals by the musical software, music instrument software. And then that will allow you to create musical notes, or try to create musical notes from a quantum computer. So from there you can actually do a setup to create the music for an audience, in this case connected to a speaker. So this is a very fun example of controlling qubits, playing around with it. And so in that example, the kind of qubits that they were using, it's a kind of transmon qubit, where you have superconducting components here, and then there's an interface between those two, and in between the two there's a, well, insulator. It might be aluminum oxide or some other oxide material, very thin. A tunnel barrier exists around this area, inside of this device. So this is a top-down view of the device with the scanning electron microscope. And then here's the cavity. There's a cavity. This is just a little chamber, a metal block that can be sealed. So this is open at the moment, but typically what they do is they close this box, and then the qubit will be contained in that box. So here is the audio frequency of the qubits. As I mentioned, you can measure the ground and excited states over time, over different samples or iterations. And then you can use pattern generation. You can use the computer code to identify, to create these waveforms. And then the waveforms, if they're moving too quickly, you can diminish the frequency into the audio range. So audio range frequency is like anywhere from a few hertz all the way up to like 20 kilohertz, which is audible for human beings. And if you were talking about animals or some other, maybe like a dog, the audio frequency for them might be much higher, maybe 40 kilohertz or something or more. So again, here's just a testing setup for such a system. You have two qubits set up here between these two systems, and then there's a bus resonator between the two, and the cavities that exist to host those qubits. And then you can try to measure the amplitude of those ground and excited states of such a qubit over time. And if this other qubit is not following that qubit, if that resonator is not working, then you will see a signal like this, and so they call it, in their case, a bad follower. But if they are in tune with each other, they are being influenced by each other, then you will have a signal that's more or less lined up like this on a plot. So when you plot that on a program like Python, then you can get these results. And then from here you can try to use these results as a way to create or generate music, and then modulate the music by connecting it to a keyboard. And here's the paper. Here's the audio samples, the music. If you want to actually listen to the music that was generated by a quantum computer, you can go to the Yale Quantum Institute here at this website. And this is the layout for how they read the signals. So the signal output comes from it's just an organizing device, the mixer, which will take a modulating signal coming from the quantum computer. So the quantum computer is creating a modulating signal, but that modulating signal needs to be decreased. The frequency needs to be adjusted so that it's at the audio frequency, audio rate, and then that audio rate frequency will create a modulator or something that will manipulate some sound generator or an oscillator. Yeah, it is a sound generator that has oscillating frequencies, and then from there you can use it to create music. So that's just how it works. In summary, we covered the different kind of qubits that are these two, that come in these two form factors, the natural atoms and the artificial atoms. Regardless of which one you build or ones that you use to create a quantum bit, you can control it by a signal pulse. A signal pulse, it can be manually you can try to do it in a semi-manual fashion, controlling a single qubit or maybe two of them, or you can try to automate it. You can automate that operation by using computer code, such as done with Python. And then the physical machine setup can also, you can try to understand the physical machine setup using neuron stimulation technology, which is part of medical, or you can use audio technology, such as we showed earlier, and even musicians who might be a bit more familiar. So if you are a musician and you know how to use electronic instruments to play electronic instruments, then you actually have a better understanding of quantum hardware than you realize. And I like to use that example. So, and then the other thing, of course, is that control hardware, it contains a lot of analog components. Many, you would consider a quantum computer a kind of analog machine, because it uses all these pure waveforms. But then the waveforms have to be converted back into a digital form for a laptop PC or desktop PC to be able to understand. So that's why we have all those converters back and forth. And then you can also try to miniaturize many of even the analog components. You can try to miniaturize all these control components using chips. You can use CMOS, complementary metal oxide semiconductor chips, to try to reduce the area of all those wires to make it less convoluted. And then you can leverage that to create a smaller quantum system so that you can save space, or maybe you can save energy in that case, because, well, cryogenic CMOS components tend to use less power compared to all these bulky analog setups. So that's the main point. So thank you for tuning in to the lecture series, and I'd like to give my thanks to Sanjay from IBM Quantum for inviting me to this lecture series, to give the lecture series. And I'd like to give thanks also to the QuantumGrad team for helping to keep the QuantumGrad quantum education material going, and also for allowing me to be a part of the community. And we also invite you to be part of the QuantumGrad community if you are interested. And we try to make content available so that people can have a greater understanding of quantum technology throughout the entire quantum stack. And with that, I will show you some bonus slides. I have 2 bonus slides to show you. So this is related to quantum jobs. So you can actually get a job. You want to work somewhere that's related to quantum computing or quantum technology in general. You can do so even as a person who doesn't necessarily specialize or have expertise in quantum technology. You can still work in this area without being a quantum expert. There are, of course, areas which you have to be a quantum expert, such as error correction scientist, or physicist, an application architect, experimental physicist, chemist, theoretical physicist, quantum algorithm developer. You kind of have to have some know-how, some knowledge of quantum technology and how it's used as far as the quantum programming, things like that, quantum software. And then also for photonics engineers, scientists, and so forth. So these areas are some they're primarily taken up by people who have expertise in quantum. However, what I say is, when I say expertise, what I mean is not necessarily that you have a complete understanding of quantum mechanics, but what I'm saying is that the person has a decent amount of experience or decent amount of knowledge about quantum technology from a technical standpoint. That's what I'm talking about. And also, there are some exceptions which are here in the orange. So you can be a data scientist, which is non-quantum, and you don't have to be a quantum expert. But if you have an interest in quantum technology, but you want to be a data scientist, then you can do so. It's fully available. And many other positions, even as a designer or as a technician in the field of quantum, or perhaps even a test engineer, things like that, or a circuit designer, or even in sales or marketing, things like these can be taken up in the quantum industry without having to necessarily be a quantum expert. But the whole point is that you are learning, and that you will continue to learn about quantum technology. So perhaps even working in these positions, you eventually will become a bit more than a quantum enthusiast. maybe it will lead you to becoming a quantum expert in the future if your interest begins to grow even stronger. So that's what this is about. And the point here is that if you want to work in the quantum industry, you don't necessarily need to have quantum expertise. You just need to have some interest. And then here's an example of problems that are solvable by quantum processors. There's a big market for doing optimization and then simulation. I would say these two are the two big ones, because both of these are related to doing manufacturing or medicine, trying to solve something that's really huge and significant to everyday life. And machine learning is beginning to be a part of that as well. So we end up having quantum machine learning approaches and research efforts, things like that. And then cryptography, on the other hand, is a little bit smaller because it's a bit more niche, and it's primarily, I would say, the governments, organizations, security organizations. They're primarily interested in that area, but the majority is taken up by all these others. So it's billions, hundreds of billions of dollars all together worth for all these applications. So that is the last slide. Here's an acknowledgement to Creative Commons License International Attribution. So just wanted to point that out. Anyways, thanks for tuning in to the lecture series once again, and it was a pleasure being able to present here. Until next time, Ada'ahulya. That means take care of yourself in Navajo. Cheerio.